So first of all, you could see here that's like an atom, all right? How do you identify an atom? Usually, the number of shells. So here I have like 2 shells of electrons. This stands for the period number. So in the periodic table, this element, lithium, must be in the 2nd period. And the valence electrons, which is the outer shell electrons, is the group number. So lithium belongs to group number 1. Number of protons is particularly important because the number of protons is the one that determines the position of the element. So it determines the position of the element in the periodic table. Number of valence electrons, on the other hand, so these outer shell electrons, these are the ones that determine the chemical properties of the element. So as long as you got the same number of valence electrons, then chemical properties won't vary. They will always be the same chemical properties. Number of neutrons could vary among members of the same element because you got something called isotopes. So isotopes have same protons, but different neutrons, right? This is the subatomic particles, the 3 of them. Their symbols, so like if you are to write it up in the exam, you're allowed to write them in this way. The charges, I'm sure you're familiar with. There is one particular case about the mass of subatomic particles. When I am to count the mass of an atom, I completely ignore the mass of electrons. So electrons' mass is way too small to consider. So for instance, lithium got 7. The atomic mass of lithium is 7, right? And it got 3 protons. So this 7 is 3 protons and 4 neutrons. So together, that's what it says. So the electrons they do have a mass, but we ignore the mass of electrons because it's way too small to be calculated. All right. So we'll move on. Definition of isotope, that's like quite important. What's an isotope? An isotope, they have to have same protons. So they have identical number of protons, same number of electrons, right? But neutrons, they're different among isotopes. So for instance, these 2 isotopes of carbon, all right? When I am to write up or when I have to determine the mass of a carbon, I really have to consider the masses of all of its isotopes. So for instance, it's a bit too shallow to say that the mass of carbon is just 12. You really have to consider the other isotopes of carbon. So for instance, in the AS periodic table, the mass of carbon is written like 12.01. The mass, for instance, of chlorine is 35.5. So where do these decimal points come from? The decimal points come from the fact that these masses here, the 35.5 and the 12.01, these are actually average. They are average masses of all existing isotopes of this element. However, for us in chemistry, we always use this version of carbon. So this is like our reference for all of our calculations. So in our calculation, even the definition of moles, if you still remember, we used carbon 12 in our calculations. All right, so this is the isotope issue, right? We have another ISO here that's new to you. there's something, there are species we usually call isoelectronic. What does isoelectronic stands for? Iso is similar. Electronic means they have the same number of electrons. So what's the definition of isoelectronic species? They are atoms or ions. So they could be atoms, they could be ions. What do they have in common? The only thing in common here is their number of electrons. So I'll give you examples of isoelectronic species. So take a look here. What I've got is some members of the periodic table. I'm gonna identify isoelectronic species here. So I'll start with nitrogen. If you look closely here at nitrogen, nitrogen got 7 electrons. So this number of electrons of nitrogen is 7, all right? How many electrons does the ion of nitrogen have? You're gonna have to look here, check its charge. So it's gonna be 7 plus 3. This means that it's 10. The ion of oxygen, so oxygen's electrons are 8. If you add 2, this means it's gonna be 8 plus 2 is 10. Same would apply to fluorine. It's gonna be 9 plus 1, and that is another 10. Neon itself, without it, neon doesn't make ions because it's a noble gas. It is also 10. Sodium ion, sodium's electrons are 11 minus 1. That's because it lost an electron here. It would be 10. 10 for magnesium, 10 for aluminium. So as you can see here, all of these here, all what I was counting, they all have 10 electrons. So these atom, there's one atom here, and all of these ions, they are all isoelectronic. All right, so one more time, what are isoelectronic species? I'll give you more examples. For instance, chloride ion here, sulfur ion, phosphorus ion, and argon, they are isoelectronic because they all got 18 electrons. All right. Generally speaking, in the entire periodic table, how you identify the isoelectronic species. So take neon and all of the anions before it, all right? And all of the cations that come after it, all right? They will always be isoelectronic. Same applies to argon. All of its anions, all of its cations that come after, they will all have the same number of electrons, all right? Do you guys have questions about this part? Do you know how to identify isoelectronic species? All right, so could you, if you have a periodic table now, can you identify letter D? Can you find what's the value of letter D? I'm gonna write you up aluminium here. It's 23, 27. So can you work out D, E, F?
D is 13.
D is gonna be 13. That's good. That's because it has the same number of protons. It's not an ion. What about E?
27.
27, good, because it's mass number. And atomic number is gonna be?
13.
That's 13, good one. Now, here they've given me 2 isotopes of oxygen, all right? So oxygen in the periodic table is gonna be 8 and 16, like this, right? So neutrons, how many neutrons does oxygen have? Is gonna be 16 minus 8. This applies to oxygen 16. What about oxygen 18? you check here, is going to be again 18 minus 8, that is 10 electrons. So you could see here between those two isotopes, the only value that will change is the number of neutrons. All right, so now if I remember, I told you that carbon exists in two versions. There's carbon 12 and there is carbon 13, right? When I want to calculate the average or the isotopic mass of carbon, remember I said it's 12.01, right? Why is this number closer to 12 than 13? This is because of something we really have to consider here, which is called abundance. The word abundance is another word for like availability or percentage. So in nature, like almost 98% of carbon is carbon 12. So when I am to find the average atomic mass of carbon, I have to consider the abundance of the elements. So I have to like think that it's not really fair to put it as 12.5 while the majority of carbon in the world is carbon 12. Now, here is another example. That's chlorine. Take a look. There is two versions of chlorine here. There is chlorine 35 and there is chlorine 37. However, the abundance of these chlorines is different. So the abundance of chlorine 35 is more. It's like 75%. And the abundance of chlorine 35 is way less. It's like 25%. So again, I'm gonna organize the data here. So we got two chlorines, chlorine, chlorine. Abundance, in terms of abundance, 75% is chlorine 35, 25% is chlorine, another version of chlorine called chlorine 37, I'm sorry. Now, how do I find the average atomic mass of chlorine here? What do I have to do? All what you have to do is to consider both the mass of each one of those chlorines and its abundance. So look at the way I do it. I say 35 times 75% plus, so this is separate, plus 25, just make it in the same order, plus 37 times 25%. Okay. Now that I've done the work here, what do I do next? I would just divide this total by 100 because the abundance of both chlorines, if you add up both abundances, it's 100. Once you do the working here, you will get the average of this average atomic mass. So look at the way I'm going to do it. I'm going to say it's going to be 35 times 75 plus 37, all right, times 25, all divided by 100. Oops, 1 second, what have I done here? 35, yeah, I need another bracket here. So once you do it, because you need more brackets here, you will get an average of 35.5. What am I going to call this number? This number is going to be called average atomic mass. So it's the average atomic mass after considering the percentage abundance of each one of these elements. All right, do you guys have questions? We're going to try this again with another case, but do you have a question on these words. What are the new things we've learned here? We learned the word abundance. So do you understand what abundance means? Do you understand what average atomic mass stands for? Any question? So these are two essential definitions we have here. There are two definitions. One of them is relative atomic mass. What does relative atomic mass? I'll stress here on atomic. This is the mean or the average of all isotopes. Now, since they said the word relative here, since it starts with the word relative, this means I have to use this reference. What's this reference we always use in chemistry? Our reference is carbon 12. So again, let's read it out again. So what does relative atomic mass stands for? It's the average all isotopes of one element compared to carbon 12. But I'm not gonna take the whole mass of carbon 12. What am I taking here? I'm taking 1 over 12. What does 1 over 12 stand for? This means I'm taking 1 unit of the total mass of carbon. So again, 1 over 12 is what we call atomic mass unit, AMU. That's the unit we use for masses. So for instance, when I say chlorines is 35.5, what is the unit for this 35.5? The unit is atomic mass unit. What's an atomic mass unit? It's 1/12 of carbon 12. What does the 12 here stands for? This is the mass of the most abundant form of carbon. All right. There's another essential definition here, which is called relative isotopic mass. Now, this is exactly the same definition, but not for this and this. No, this one is for one individual isotope only. So one more time, those two definitions here, we have relative RAM, relative atomic mass. This is average of all isotopes. What's the scale we use here? The scale is 1 over 12 of C12. So the 1 over 12 is the individual unit, and C12 is our reference in chemistry. And relative isotopic mass is the mass of one isotope. Notice I don't have average here. There's no, the word average doesn't exist for one individual isotope. All right, do you want me to repeat this or it's fine? Is it okay? All right, let's try this question. The hydroxide ion has a total of 9 protons. So OH negative has total of 9 protons. How many neutrons, electrons does this ion contain? Can you figure out like how many neutrons, electrons does OH negative have? So O in the periodic table is like this. 8, 16. Hydrogen, the periodic table is 1, 1. So which one of these is the right answer?
B.
You think it's B. Anybody else has another opinion? Any other opinion here? It is actually B. Why is it B? That's because O in the periodic table is 8, 16. So protons for oxygen is going to be 8, right? protons and electrons are identical for oxygen. So 8 electrons. What about hydrogen's electrons? How many electrons does hydrogen have? Hydrogen has only 1 electron, right? So electrons for hydrogen is going to be 1. So O and H. Electrons for oxygen is 8. Electrons of hydrogen is 1. Neutrons for oxygen is going to be 16 minus 8. That's an 8. All right. Neutrons for hydrogen is the only element that doesn't have neutrons because it's going to be 1 minus 1. So 1 minus 1. So that's a 0 here. All right. So this makes it total, all right, for electrons going to be 1 here. So sorry, it's going to be 8 plus 1. It's a 9. And 8 plus 0 is 8. I have to consider this negative charge here, we notice. All right. So this, you add this to the 9, it becomes 10. All right. So that's where the 10 comes from. You're going to have to add 1 extra electron because OH has a charge of -1. All right. So another question. Use the periodic table to find which one of those two are isoelectronic. All right, so lithium. Any answer first? Or am I going too fast? So Li is 3, 6. Oxygen is 8, 16. Sodium is 11, 23. Chlorine is 17, 35.5. Magnesium, 12, 24. Sulfur, 16, 32. All right, last one, aluminium, 13, 27. Fluorine, it's 9, 19, right? So which two of these, which pair are isoelectronic? What do you think?
D.
D, yes, is D, because aluminium is Al3 plus. Fluorine is F minus. So 13 minus 3 is 10. And 9 plus 1 is another 10. So you see, just determine their, you could, by the look of the periodic table, it's much easier if you just look at them in the periodic table. Aluminium is somewhere here. Neon is here. And F is here, all right? So always, anions are isoelectronic to next noble gas. Just remember this. And cations are always isoelectronic to previous noble gas. All right, so that's always the case.
Sir?
Yep.
I really don't understand what isoelectronic means.
Iso means same.
Mm-hmm.
So iso is same. Electronic means electrons. All right. Mm-hmm. So when I say isoelectronic, this stands for elements that have identical number of electrons. So aluminium, if you take a look at aluminium here, right? Aluminium is losing 3 electrons. If you see 3 plus, this means it lost 3 electrons. If you see F minus, this means it gained, right? Gained 1 electrons. Good. Okay. Now aluminium in the periodic table has 13 electrons. All right. What if it's losing 3? How many electrons does it have? What do you think?
10.
10. F in the periodic table F in the periodic table is 9, all right? It's gaining 1. This means it's having 10 electrons. If you try this here, try this for lithium and oxygen. Lithium is
7.
3 electrons originally, right? And oxygen is 8 electrons. So can you figure out like how many electrons does the ion of lithium have?
2.
2. What about oxygen anion here? How many electrons does it have?
10.
10. So they're not isoelectronic because they have different number of electrons. Okay.
Thank you, sir.
Again, one easy way without calculations is just take a look at the periodic table, and always the cation will have same electrons as the previous noble gas. And the anion will always have the same electrons as the next, or the noble gas that comes right after it. Okay? Do you have a periodic table in front of you?
Yes.
Do you know magnesium, which noble gas is magnesium isoelectronic to?
Magnesium.
Previous, right? So the noble gas that just comes before magnesium.
Chlorine.
Neon. Neon is a noble gas. Yep. Sulfur will be just like the next noble gas. The next noble gas to sulfur, the one that comes right after it, is argon. You see here, they're not isoelectronic. Okay? Are you following?
Yeah.
All right. Can you try sodium chlorine? What's the noble gas? What's the how many electrons does sodium ion have here?
10.
It will be like the previous noble gas. Previous noble gas to sodium is neon.
Oh.
The next noble gas to chlorine, chloride ion, is going to be argon. So they're not identical. All right, so an atom and an ion with a single positive charge are isoelectronic. Therefore, what's the conclusion here? What do you think? What's the right answer? What do you think, guys?
C.
Atomic number is 1 more than the ion. To work it out, I will just take an example. So the atom and ion have the same mass number is not, that's wrong, right? Have same atomic number is wrong because atomic number is proton number, right? So that these A and B are definitely wrong. Those C and D are pretty confusing. So what do we do here? Take Na plus, right? And take Ne. So atomic number of the atom is 1 more than the ion, right? That doesn't work here because the atomic number of neon is 10. The atomic number of sodium is 11. All right, so atomic number of atom is 1 more, is the other way around, isn't it? It should be the atomic number of the atom is 1 less than that of the ion. Again, why did I use sodium as an example? Because the question says single positive charge. So since they said single positive charge, this means I have to pick a member of group number 1. I could try another member of group number, I could try lithium. So lithium is +1. What's the previous noble gas to it? Is helium. Lithium got 3, the atomic number of lithium, and helium's atomic number is 2. So it works everywhere. It works for every single positively charged atom and ion. Do you have a question here? So take any one of your choice, and it will always be like this. That's 18, that's 19. All right. One last question. Could you guys work out the total number of electrons for carbon dioxide and try to match it with one of these? So total electrons of carbon dioxide and match it with the total number of electrons of these. So carbon is 612, nitrogen is like 7, 14. Any idea? So total is gonna be 6 and 8 times 2, isn't it? That's because I'm counting electrons. So total number of electrons of carbon dioxide is gonna be 24. These are all the electrons of carbon dioxide. Which one of these has 24 electrons?
Sir, I think it's 22, not 24.
You sure?
Yeah.
6 plus 16. Oh yeah, you are absolutely right. Yeah. 6 plus 16 is 22. You're right. So which one of these is 22?
A.
It is a good one. All right. Last question in this series. Which statement about subatomic particles is correct? That's the easiest. So can you figure out?
A.
Good one. Very good. All right. So we're done with this section. This section was like mostly things you've taken in the past, except the isoelectronic particles. We're gonna start with something new. This is like a machine that we use to separate particles. Mainly we separate, in this unit 1, we separate atoms and isotopes. So this machine's name is called the mass spectrometer. So mass spectrometer. How does it work and what is it used for? Basically, you take a sample here. So you take a sample of a rock or a piece of cloth or urine samples, and you run it into the machine. Several stages here. You have one of the stages, you turned it to ions. The second stage, you will deflect those ions. I'm gonna go into all details until you detect what is there in this sample. So again, what's this machine used for? It's used for something called carbon dating. What is carbon dating? Carbon dating means mainly like you find the age of bones or whatever sword or whatever you found. You could use it to detect illegal drugs, like athletes cheat with their urine samples. They could take drugs to enhance their performance. So you could identify what elements they're found inside their urine. It's used to forensics, means like it's used to find like things you find in a crime scene or something. And it's also used to identify meteorites or anything you find in rocks you got from the space. We're not really like concerned about these, but if they asked you, which they've done in the past, if they've asked you, what's this mass spectrometer used for? Just learn 2 or 3 of these uses of the mass spectrometer. So right now we're gonna learn how this machine works. Can keep in mind these steps. So what are the steps here? Step number 1 is vaporizing. So if you got a rock or you got a piece of cloth or you got urine, you must turn the sample into gas. So we take this sample and we vaporize it under low pressure. Then we turn it to positive ions. We call this step ionization. Following this, what are we going to do next? We're going to speed up the sample. We're going to accelerate the sample. We're going to use electric field. And finally, we're going to use a magnet to deflect the particles we got in this sample. And then we detect it using a computer screen like the one we have here. So let's start with the first event. First event is vaporization. Okay, so here's my machine. So event number 1 is I'm gonna get the sample and I'm gonna vaporize it, meaning that I'm gonna turn it into a gas sample. Reason why I need it to be in the gas stage, it's because I cannot run into this machine. I cannot run solid or liquid forms of matter. I need to have gases because I'm aiming to run this sample throughout this tube that you can see here in my machine, all right? Next event is ionization. How am I gonna ionize? I'm gonna hit the sample, I'm gonna hit the particles in my sample, I'm gonna hit them with an electron gun, like the one you see here. As you hit them with this electron gun, you're gonna knock out some of the electrons that you got into your sample, all right? So this stage here is known as ionization. Again, how does ionization work? Ionization is quite simple. Take an atom, and what do we hit it with? We bring a gun, and we shoot electrons. As you shoot electrons on an atom, some of the electrons that exist in your atom get knocked out. So those electrons that I'm shooting with, I'm gonna color blue. And those electrons that I'm knocking out, I'm gonna color red. So for instance, if I had an atom of sodium and I hit it with a blue electron, what do I get? I will get sodium ion, and I will also get my red electron and my blue electron. What's the difference between the blue electron and the red electron? Blue electron is the one I shot the atom with. It reoccurs here on the right. The red electron is the one that the atom has lost and is becoming an ion, right? Any question about ionization? Do you want me to repeat it? So now the sample is in the gas form and is completely being ionized. So every single atom that I have has basically turned into an ion. What am I gonna do next? What am I gonna do next is that I'm gonna bring it here and I'm gonna accelerate. How am I gonna accelerate? I will accelerate by using some electric plates. Do you see those two plates? One of those plates is gonna be positive and one of them is gonna be negative. Remember, my sodium ion is positive, right? So the plate behind will repel because positives repel each other, and the plate in front will attract. And you could see here that it got some hole or slit. This will allow the passage of the particles after they've been accelerated. So I've turned this gaseous sample into ions, and then I've made it run very fast. What is going to happen the next stage? Next stage is called deflection. So this is my series of events. Now I'm here. I'm deflecting what I've accelerated. So next event, I'll bring the magnet, huge magnet like this one here, and I'm gonna deflect this sample. So the charged particles can be easily deflected, all right? Now, the degree of deflection is something to worry about. What will determine like how much deflection my sample will have? The degree of deflection will depend really on the mass. All of my particles have 1+ ion. If the mass of one of the species that are running here is heavier, it will deflect less. If it's lighter mass, it will deflect more. I'll give you like an example here. If I have two samples, one of them is red and one of them is green, all right? Both have identical charges. The mass of this is 15 and the mass of green is 6, all right? And I'm running these into a magnet like this, okay? Now imagine these are two cars, okay? This is red car, this is green car. Which one of these can be deflected more? Is it gonna be the red car or the green car if you're applying the same force with your magnet here? So what do you think? Which car, which is it gonna be the red or the green is gonna like be pushed further?
Green.
It's the green. Usually, yeah, lighter objects, if you apply the same force on two objects and one of them is lighter, then it's gonna be deflected more. So the whole principle of your mass spectrometer is based on this thing. If you have two ions that have identical charges, the ion that is lighter will deflect more. And finally, what do I do here at the end? I have like a fluorescent screen, like the one you have in all TVs. The ion comes here, and since they have different degrees of deflection, they can be detected on the screen at different positions. So each ion will be, so like lighter one will be detected on top, heavier one will be detected at the bottom. And then I could use my computer screen to detect the position of these ions after they have lost their charges on this screen. All right, so let's first try to put the events in order, and then like we revise this whole mass spectrometer thing. So which we expect to be the first event here?
C.
Event C is number 1, all right? Then what was the second event?
B.
Then it's second, number 2. What have we done to the ionized particles then?
D.
Then we've accelerated, and then we've deflected. Finally, we've detected them, right? So first event, we took the particles, right? We've turned them into ions. Then we run them into slits like this. One of them has like, they have negative charges here. It gets attracted, and one of these plates here has positive charges. So the ions run really fast. Then I have a magnet, north, south here, that deflects them based on their masses. So the heavier, the less the deflection is. And finally, we detect those ions. How do we detect them? We detect them here on a screen. So the degree of deflection, right, will let those ions drop on the screen at the end at different positions. And from this angle of deflection, I could detect the position of these ions. Right? Could you guys try to match each definition with its like function? So I'm gonna number these 1, 2, 3, 4. And I'm gonna put letters here, A, B, C, D. So what does ionization stands for?
A.
It is that's when we use the electron gun to shoot and knock out electrons. Acceleration. What did we use to accelerate?
C.
Then it's C.
B.
Deflection, we use the electromagnet, right? A. And then finally we detect them. 1 second, I think
Isn't
we've
to
just a sec. So we've first took this. Acceleration is this, right? With B. Attracted, so that's the. Then we've deflected, all right? How did we deflect? With the magnet. And finally, we've detected it, right? With this final plate, right? So there's a final screen here, we called it. What's the screen for? The screen, they lose the charge and we could detect them there at the end. All right, so I have the parts of the mass spectrometer with the letters, and you guys need to determine like what letter is for what job. So detection occurs at which letter?
E.
That is E, it's here. And acceleration is which letter?
C.
That's C. And then we got, where do ions get separated? Where do we separate the ions, basically? What do you think? Which part is to separate?
Is it D?
B is the gun, right? B is gun. D is where we separate the magnet. Magnet is to separate. All right. Then we got where an electric field is applied. Where do you apply an electric field? Where do you think?
C.
C is the plates where the electric field is applied. Where do you create the ions? Where are ions made?
B.
B is the electron gun. Yeah, that's where we create the ions. Vaporization is easy. It's like the first thing. That's where we, yeah, A. And magnet is where you separate it. Finally, which one is this? Where do ions lose their charge? Not gain charge, lose charge. They gain the charge here when they're ionized. Once they hit the final plate here, the screen where you detect them, that's where they lose this positive charge. So they will lose the charge, and that's like where the current runs in the machine. All right. Now, what do we use this mass spectrometer for? Now, as you can see here, the graph is what we get on the screen. So if you had the machine, the screen at the end will show you something like this. All right. And what do I see here? It's a graph of abundance versus M over Z. What does M over Z stands for? M is mass, Z is charge. So the mass and the charge of the element. Now for us in AS, the charge is always going to be 1 plus. All right. So unless you've been told otherwise, your charge is always going to be 1 plus. So basically, the values on the x-axis is just like the atomic mass or the molecular mass of the species. What about the y-axis? The y-axis is the abundance. Abundance is the percentage in the sample. So let's say your sample is that much. 80% of your sample, of your urine sample or your gaseous sample, is boron 11, and the rest of it is boron, 20% is boron 10. How do I work the average atomic mass of boron based on these? What do? As I've done earlier, I say 11 times 80 plus 10 times 20, right? All divided by 100, because the total abundance of these two species is going to be 100%. And then from this, what do I get? From this, I will get the average atomic mass of boron, or relative average atomic mass of boron. All right. Could you try this? So the answer for what I've done here is going to be that much, 10.8. I want you to try this question. It's about magnesium. And you could see here that there is 3 isotopes. Let's try 2 isotopes first of sulfur, and then we try the 3 one. Could you try this question and figure out like which one is the right answer? So here you got 2 isotopes of sulfur. One is 96% and one is 4%. And the masses are given in the symbol of the element itself.
Okay.
So you worked it out, turned out to be you did 96 times 32 plus 4 times 34. And you divide it by 100, and it's 8. I don't think it's that hard. It's always going to be this way. You find the average. Do you guys have a question? Can you try the magnesium one now? This one here, they want you to find, they used 3 isotopes of magnesium. So I'm going to color code them for you. This and this. All right. I think I've messed it up. So again, one more time, the 79% is 24. The 10% is this. And the blue one is this. Any luck?
24.32.
24. So let's check the working. Yeah, you're right. All right, always take the same number of decimal points as the question itself. Someone asked you here to name the processes at B and C. What do we call what is happening at B? Can you just take a look and tell me like what process is happening at B?
Acceleration.
That is acceleration. What is C called? What event occurs at C?
Deflection.
Deflected. So you deflect with the magnets here. All right. They've said here complete electronic configuration of potassium K39. All right, so K39, atomic number is 19. Who's gonna do that first row here? Electrons?
Electrons, 19.
Yep, 19.
Protons,
Protons?
19.
19. Neutrons,
20.
39 minus 19. So that is like 20, right?
Yes.
The other guy, what are the things that's only supposed to change here?
Neutrons.
Neutrons. So what do we change here? So this becomes like 22. And that's 19, 19. All right. Now, if you still remember electron configuration, what's electron configuration? It's like how do you distribute electrons? Electron configuration, we used to put 2 electrons here, all right? And we were allowed like to put up to 8 electrons for any other electron shell. And we always used to say like outer shell electrons are the valence electrons, those are the ones that determine the chemical properties. This year, we just want to elaborate on this electron configuration. We want to add some extra things. If you've ever had a chance to watch how electrons really are, electrons are like this. There are blinks of light. If you see on your screen, these blue waves here, these are how electrons are. So electrons are like nothing like what we draw on papers, right? So they're like waves. Electrons have both a wave nature, like light nature, and particle nature. For that reason, scientists, physicists, they've come up with this definition. This definition is known as orbital. So what's an orbital? Instead of saying orbit, this year we're going to say an orbital. An orbital is a region inside an atom, somewhere around the nucleus, that holds up 2 electrons. And these electrons that are held up around the nucleus, they're in opposite spin. So let's explain this definition. So again, how do you identify electrons? Since they run really fast and they're more like waves of light, it's really hard to determine where an electron is. So they came up with this new definition. We called it orbital. An orbital is like somewhere around the nucleus. So let's just go back to the diagram here. It's somewhere here, anywhere in this blue area that I'm shading, where it's very likely, where the probability or the chance of finding electron is high. And we always assume that electrons are spinning either clockwise or anti-clockwise. So instead of drawing electrons the way we used to draw them in the past, we're now going to approach a more realistic way of showing electrons. We're going to show electrons as arrows, and these arrows are spinning. They could be spinning this way or the opposite way, right? So that's the new thing about we call orbital, right? We're also gonna just spend time doing this thing here. We're gonna divide the periodic table into blocks. We're gonna divide the periodic table into 3 blocks. One block we're gonna call it S, one block we're gonna call it D, and one block we're gonna call it P. Now, the electrons in the S block will always spin the atom in the shape of a sphere. So if you are to track an electron running around the atom, and this electron was found among members like sodium, lithium, hydrogen, whatever, the electron will always spin the atom like a sphere. That's where the letter S in block S comes from. Electrons in this block, like chlorine, neon, and all of these elements, they found that this electron spins the atom like this symbol. in chemistry, we call this symbol, we call it dumbbell shape, like the gym dumbbell shape, or it looks like an infinity sign. What about d electrons, like iron and all of the transition metals? We're not really, the shape is way too complicated. And we're not gonna really like spend, it's not our syllabus to determine the shape of electrons in the D block, right? It looks complicated at the beginning, but promise it's much easier when you're try to look at it this way. So I'm gonna show you how electrons are like in an atom of hydrogen. Why I picked hydrogen first? Because it's like the simplest atom ever. Electrons there's only one single electron in hydrogen, and this electron is spinning. It could be spinning clockwise, anti-clockwise. If you track this electron here, how will it look like? It will draw you the shape of a sphere, something like this. So if this electron has a trail and you're tracking this electron, the electron will draw you the shape of a sphere like this. I'm gonna jump to the second element in the periodic table, which is helium. Helium, the electron in helium, there are two electrons. How are these electrons gonna be like? They're gonna spinning opposite directions. And again, if you are tracking these electrons, they're gonna draw you the shape of a sphere as well, because hydrogen, helium, they belong to the S block. If you look at my periodic table here, I always, when I am to draw the electron configuration, I move helium from here and I drop it here. So those are all elements in the S block, everybody here. Now let's go to the next element in the S block. Now I'm gonna go to lithium. How many electrons does lithium have? Lithium has 3 electrons. So when I am to show the electrons of lithium, check, I have 3 dots. So I'm gonna just zoom in here closely. What do I see? I see 1 electron here, 1 electron here, and there's a 3rd electron spinning outside. This means what? This means that lithium has now 2 shells. It has first shell. Let me show you how to write lithium. It has the first shell called number 1, shell number 1. It's S. Why is it S? Because lithium belongs to the S block. How many electrons do I have in the first shell? It got 2. So when I write, for instance, if I am to write hydrogen, how do I write electron configuration of hydrogen? I write it 1. It's the first shell. S1, that's hydrogen. Now, what if I want to write helium? What do I write? I write He1, S2. There's 2 electrons in helium. If I am to write lithium, what do I write? Lithium got 3 electrons. How do I write lithium? Look at the way I'm going to write it. So I'm going to come here to the periodic table and I will spot lithium here. Where is lithium? Lithium is like hydrogen. Helium, lithium. How am I going to write lithium? First of all, I work out its position. It's first period, second period, right? Therefore, lithium is 2. Do you remember what we called this block? We called it S. So we're going to call it 2S. How many electrons does lithium have? Lithium has 3 electrons, right? 2 electrons are already covered in its first shell. So the first shell of lithium is 1S, right? How many electrons do I have in the first shell? It's 2. The second shell of lithium got only 1 electron. So I'll do this one more time. It's the easiest way to do it is to use the periodic table From the periodic table, you can work out the electron configuration of any element of your choice. So for hydrogen, which is the very first element in the periodic table, what do I write? I write 1, 2, 3, 4, and so on. Hydrogen is here, is in the first group. Helium is in the second group. So if I am to write hydrogen, how I write it? I write it 1. Which block? It's S. Which group? It's 1. What about helium? How do I write helium? Again, 1. Block is S. How many electrons? Is 2. If I am to write lithium, what do I write? I write 2. Block S. Group is 1, right? Can someone figure out like beryllium? How do I write electron configuration of beryllium? What will it be? It's gonna be 2. Why 2? Just because period is 2. S is the block, and the group is what? It's in group 2. Can someone try, please, the element sodium, which is found right here in this blank?
3s1.
So it is gonna be 3s1. Can someone else other than Amar try magnesium here? How do I write magnesium?
3s2.
3s2. Now, what if you've been asked to identify an element from the P block? So this is called P block, we used to remember. How will I identify elements from the P block? I work out the period number. So what period number I'm gonna start with? Check here. I don't have, this is blank, all right? So this is empty. We actually even moved helium from here. It doesn't belong here anymore. So let's try boron. What do? I number the P block, I number it separately. 1, 2, 3, 4, 5, 6. All right. Now, what do I do here? I say it's gonna be P, because it's in the P block. Which period am I in? I am in 2. All right, so that's period 2. And which group in the P block? It's group number 1. All right, so that is gonna be the electron configuration of boron. All right, the element that comes right next to boron is carbon. So it's gonna be again 2. Why is it 2? Because I'm still in the second period of the periodic table. 2, block is P, group is 2. All right. Can someone please try aluminium right here? Can you figure out like what the electron configuration of aluminium is going to be? So I'm now want to work out aluminium. Is this question mark? What will it gonna be? So I'm just gonna clean up here and write you the periods. 1, 2, 3. What will it be? So first thing, you write the group number, the period number. What period am I in here? It's gonna be 3, that's the 3 here, okay? And then you write the block, which is P, and then you write the group number. Now, I don't want you to write these things without understanding what do they mean, right? So let's try to understand what do those S, P, and the numbers we're writing for, what do they actually stand for? They stand for S. So for instance, if I write 3S1, the 3 stands for the shell. So the 3 is the shell. The S stands for the shape or the sphere that the electron is drawing while it's rotating around the nucleus. And this number 1 here, what does it stand for? It stands for the number of electrons. How many electrons do I have? So for instance, here, I have one single electron, right? So if I'm writing like say 3p2, 3 stands for the shell. How many shells? I am drawing 3 shells. P stands for the trail of electron. What shape is this trail of the electron? And 2 stands for how many electrons you got there for this element. I'm gonna repeat this thing all over again next class because we just like did an introduction today. So we're gonna start over with this thing next class. And for next class, I want you to prepare, all right, for a test on chapter number 1. So expect questions about moles, counting atoms, and volume of gases, all right? If you have prepared already for the test, then just stay behind and I give you the test right now if you don't want to drag it for the next week. If you're not ready yet, then you could take it next week.